Today we are going to see a case study on vector calculus. Introduction. With the growing robotization of production and management processes in the modern workplace, only high quality education and training will lead workers towards enjoying secure employment and a stable income, orienting towards a future that features extensive automation, pursuing STEM disciplines, science, technology, engineering, and mathematics, is highly promising and should be rewarding. It is important to note that regardless of whichever STEM discipline a student pursues, mathematics is a must as it is the gateway to all STEM careers. In this situation, 2-year colleges play a special role. They allow an individual relatively quick and inexpensive entry to a new area that is attractive, ensures good wages, and fits the desires and abilities of the individual. We may recall Steve Jobs saying, "A way should be found to train more American engineers." Apple had 700,000 factory workers employed in China, and that was because it needed 30,000 engineers on suit to support those workers. These factory engineers did not have to be PhDs or genius. They simply needed to have basic engineering skills for manufacturing. Tech school communities for manufacturing. Tech schools, community colleges, or trade schools could train less. Isaacson research experience adds even more value to the education and training. We conducted this research at a 2-year community college that is an integral part of a large city university. The parent university serves more than 500,000 students who attend its 24 colleges. This college offers 29 associate degree programs and 5 certificate programs. Its students can continue to associated 4-year colleges or baccalaureate studies at other institutions with easy keeping all of their earned credits. The college has specifically designed programs to support the students' education and to provide mentorship as well as financial aid. The research participants were selected on a voluntary basis from the pool of the first author students who took part in these programs. These students expressed interest in mathematics and were willing to study beyond the requirements of the curriculum. They were pursuing varying engineering disciplines, and by the time they joined our research, they were either taking Calculus 3 or continuing their mathematics preparation. Project. Curvature of implicitly defined curve in plane. This section presents explicit formula for finding the curvature of curves in plane defined as implicit functions in rectangular or polar coordinates. Initiatively, the curve measures the most of curving as a point in tracing the path, thus presenting to what extent a path of curve differs from the straight line. The curvature is an inverse of radius of oscillating circle that is tangent to the curve and provides a second order of contact with a curve. A tangent line provides just a first order contact. The curvature together with the speed determines the normal acceleration and thus the centripetal and centrifugal forces occurring in the process of the motion. These properties of the curvature explain the importance of enhancement of the techniques of its computation for different ways of the curve's definition. Geometrically, the curvature may be defined as k is equal to modulus of del phi by ds. where k is a curvature, phi is the angle of inclination of the tangent line, d is the differential of the length and symbol. Modulus of dot stands for the absolute value. Thus, the curvature determines the rate of rotation of the tangent line. The precise definition of the curvature is as follows. K is equal to modulus of dt divided by ds, where t is the unit tangent vector and symbol double mod dot is the Euclidean norm of a vector. That is, t of t is equal to r dash of t divided by Euclidean mod of r dash of t, where r of t is the position vector and t is a parameter tracing the curve. We assume that both r of t and r dash of t are continuous functions of parameter, so that the curve is tracing in one direction. For the curves in plane, the following formulas for curvature are in use. If a curve is defined parametrically as x is equal to x of t, y is equal to y of t, a less than or equal to t less than or equal to b, then we have the following equation, where differentiation is with regard to parameter t. If a curve is a graph of continuously differentiable function y is equal to f of x, then we have the following. K is equal to modulus of f double dash of x divided by 1 plus f dash of x whole square whole power 3 by 2. Finally, if a curve is defined in polar coordinates, r is equal to g of t, then we can think of it as a parametrically defined curve with parameter theta. X is equal to g of theta cos theta, y is equal to g of theta sin theta. Applying this in the previous equation, we get the equation as k is equal to modulus of 2 into r dash of 2 plus r square minus r double dash divided by r square plus r dash whole square whole power 3 by 2. It may be mentioned that the formulas 5, 6 and 9 follow directly from a more general case for the curve in space considered in Wienerski. Our goal in this paper obtain the formulas for curvatures in case when a curve is given implicitly as an equation in two variables in either rectangular or polar coordinates. Consider the rectangular coordinates first. In case a curve is a set of points satisfying an equation f of x comma y equal to 0, where f of x comma y is twice continuously differentiable function with fx square plus fy square is not equal to 0, where lower index of x and y start for partial derivative with respect to x or y correspondingly. Due to the above condition, in the neighborhood of each point x comma y, each defines either y as a function of x if f dash of y not equal to 0, or a function of y if f dash of x not equal to 0. Assume for the sake of brevity that f dash of y is not equal to 0, then dy by dx equal to minus fx divided by fy. We have the following substitution. This formula holds all if we assume f dash of x not equal to 0. That follows directly from its symmetry regard to the variable x and y, and the known fact from fxy equal to fyx. Consider now case of curve in plane given in polar coordinates by equation g of r comma theta is equal to 0, where g of r comma theta is twice continuously differentiable function with gr square plus g theta square. In this paper, we focus on more practically important case gr dash not equal to 0, when equation defines r as a function of theta in the neighborhood of each point as given by the formula. Proceeding in the case in the same way as above by using formula, we get dr by d theta is equal to minus g theta by gr. Same way d square r by d theta square can be assumed. Substituting these expressions into the formula, we obtain the preceding formula. These formulas provide an explicit expression for the curvature of a curve defined implicitly by the equation. For the case gr dash equal to 0, we consider a situation when dou of g of r theta by dou r is equal to 0, including the possibilities of a is equal to minus theta or b is equal to theta. In such case, for any r1 and r2 inside the line segment a comma b, the mean value becomes g of r2 comma theta minus g of r1 comma theta is equal to dou g of epsilon comma theta divided by dou r into r2 minus r1 equal to 0.